The essential definition of emergence is captured in the notion the whole is greater than the sum of its parts. In other words, the whole emerges unpredictably from the working relationship of its parts. Again, we see the ubiquitous and mysterious entity of randomness rearing its head in the unpredictability of emergence of properties from lower-level properties. Through the lens of supervenience, one could still claim that the A properties supervene on the B properties, but given the B properties, one is not able to predict the A properties. The classic example is the phenomenon of consciousness. Given the B properties, namely an intricate network of neuronal connections in the human brain, it does not necessarily follow that consciousness should manifest itself, thereby creating a sentient mind. At Stanford University, the physicist and Nobel laureate Robert Laughlin defines emergence as a collective principle of organization that gives rise to a law, but the law vanishes away into nothingness when you examine all the parts to see where it came from. This eloquently captures how reductionism fails to understand the whole interacting system in terms of the individual parts and pieces that make up that system. There are two forms of emergence, weak or epistemic emergence and strong or ontological emergence, with the only difference being that strong emergence has causal efficacy while weak emergence is tantamount to epiphenomenalism. For example, the philosopher John Searle holds that consciousness is physically reducible but not ontologically reducible. This implies that consciousness itself has no additional causal powers over and above the causal powers of the brain and its processes. He would have us believe that consciousness is an epiphenomenon and that mental processes have no causal efficacy, but are rather like a froth on an ocean wave, and ride along with the underlying subvenient physical processes. Consciousness would be nothing more than a phenomenon hanging off the engine of causation. On the other hand, those that hold that we conscious human beings have free will implies that emergent consciousness has causal power to change things in the world. Those changes in the world wouldn't have happened had the conscious mind not chosen to make those changes. For example, the cognitive psychologist Donald Hoffman observed that suppose you internally deliberate and decide that on a particular date and time you will observe a gravitationally lensed object, such as the quasar behind the Einstein cross. Consider just one of the photons before you observe it. That photon is in a quantum superposition of 4 trajectories around the foreground galaxy. And yet once you, a conscious entity, measure the photon by observing it, the superposition collapses and the conscious decision you made caused the photon to take one particular path around the intervening galaxy, a path that is 8 billion light years long. This is an example of strong emergence, top-down causation in which supervenient properties are changing subvenient properties and not the other way around. We can view supervenient properties as information that can be stored as patterns in matter, as in accordance with Landauer's principle. And these patterns can computationally evolve and affect the underlying subvenient matter. Patterns can push matter around, and this pushing of matter can increase entropy in accord with the second law of thermodynamics. A beautiful and compelling example of Landauer's principle is cellular automata. A cellular automaton is a computational model where a grid of cells, each with a finite state, simultaneously update their state based on the states of their neighboring cells using a set of predefined rules. In Wolfram's categorization, the Rule 110 cellular automata has been proven to be a universal Turing machine. Looking at successive applications of the Rule 110 cellular automata mechanism, the system appears to be on the cusp of chaos. Some parts appear regular and deterministic, while other areas appear random and chaotic. But if we zoom out, we begin to see structures known as gliders and oscillators, and other such macro-scale entities. These higher-level structures follow another set of rules which has been shown to be equivalent to a universal Turing machine. This means that at this higher level of description, deterministic computational laws emerge, and these high-level laws will always hold. An obvious and profound question here is, which direction does the arrow of causation point here? Since the higher-level structures, such as gliders and spaceships, must necessarily implement a universal Turing machine, are they determining the states of the lower-level properties? That is to say, are the high-level computational structures determining which cells are active or inactive? In line with Robert Laughlin's definition of emergence, when we try to determine how universal computation arises from the workings of Rule 110 in terms of individual cell activations, the explanation or reason evaporates away. Today, large language models, or LLMs, behave in the same enigmatic way. When we try to understand how LLMs actually work by digging into operations of the individual neurons, the explanation vanishes away. All that AI researchers know is that scaling up simple neural networks into large parallel processing networks somehow and mysteriously enables the system to emerge understanding and a coherence that was not in any of the parts. Indeed, since cellular automata are Turing-complete, imagine programming a multi-billion parameter LLM using a huge Rule 110 cellular automata, then attempting to reductively understand how the LLM works by examining the individual cell states, an utterly futile enterprise, as will be evident in Chapter 11.